Hello, everyone. Welcome to this EERI Northern California chapter webinar on recent aftershocks from the 2011 magnitude 9.1 Great Tohoku, Japan earthquake. I'm Maggie Ortiz Milan, Program Manager at EERI, and today's webinar is being recorded, and information about how to access the recording will be sent in a follow-up email. For those who may not be familiar, I want to say a few words about EERI before handing things over to today's moderators. The Earthquake Engineering Research Institute is the leading organization bringing together those dedicated to reducing earthquake risk. EERI has been bringing people and disciplines together since 1948. By joining EERI, you become a member of our global network of multidisciplinary professionals. Now I'll turn it over to Volkan Seviljan to let you know more about the EERI Northern California chapter.
Hi everyone, I would like to welcome you to the presentation hosted by the EERI Northern California chapter. Our Northern California chapter is dedicated to reducing earthquake risk in Northern California, especially in Silicon Valley and San Francisco Bay Area. And we have a very diverse group of members, ranging from seismologists to earthquake engineers to city planners to other professions. So I encourage anyone who would like to join us and contribute their expertise to our growing numbers of members. Please do so. If you would like to get information about the future presentations, please email Bruce Mason, who is our secretary and treasurer of the chapter. And one big announcement, now we are clear to have in-person social events. We will be organizing one of those quite soon. And next month, we are trying to get another quick quake briefings about Samos Izmir earthquake that caused a lot of damage in both countries, in Greece and Turkey. So we are lining up the presenters, and then we will announce that date as soon as we figure it all out. So I would like to now introduce you Bruce Mason, who's going to be our moderator, and he is our secretary and treasurer of the chapter.
Thank you, Bruce. Volkan. Thank you. I'd like to welcome everyone to our briefing number 5. This will deal with the large earthquakes that occurred offshore Japan earlier this year. But first, what I'd like to do is amplify a little bit about what Volkan mentioned. That is our next briefing we're planning for August. It is a magnitude 7 earthquake that occurred in the Aegean Sea in between Turkey and Greece. The earthquake collapsed buildings and took the lives of over 100 people. What's an interesting aspect of this earthquake is the epicenter is in disputed waters between Turkey and Greece, so the subsurface investigations have been very limited. Since the earthquake, Greece and Turkey have expressed the need for cooperation to learn more about the seismology in this region. So this is a very interesting aspect. We are planning to have speakers that talk about the seismology and damage, but also touch upon the cooperation that was an outcome from this earthquake. Now back to today's briefing. In February and March this year, there was 2 large earthquakes, magnitude 7, that occurred offshore Japan. A very interesting aspect of these earthquakes is they are aftershocks from the Great Tohoku earthquake, the magnitude 9 earthquake that occurred 10 years ago. So we have 2 presenters from Japan's National Research and Development Agency that'll be presenting today. But here's our format. So each of our speakers will talk for about 20 minutes each. And then at the end, we'll have a question and answer period. You, the audience, can ask questions by hitting the Q&A button. You'll see it on the bottom of your screen. You type that button and then you type in your question. And then Volkan, behind the scenes, will sort through these questions. Then he will come back later and he will pose the questions to the audience. Now, We recognize there might not be enough time for us to handle all of your questions. So both of our speakers today have kindly provided their email addresses, and they will be on their slides that they showed today. So if we cannot get to your questions today, feel free to email them, say tomorrow, and they may answer them. What I mean is they are under no obligation to answer all of the questions. And the reason is it might be too difficult. That's a joke. No, the reason is they're busy people. And if they get too many questions, they might not be able to get to all of them, but they'll be more than happy to answer some of them. So what I'd like to do is introduce our first speaker today. Dr. Seiko Kita is a senior research scientist dealing with seismological aspects. She is currently a visiting scholar at the University of California at Berkeley, and she is joining us today from Berkeley, California. She will talk about the seismology of the recent earthquakes and their relationship to the great Tohoku earthquakes. So let's kindly welcome Dr. Kita. Dr. Kita, could you please proceed?
Thank you, Bruce, for your introduction to me, introduction of me. So, can you see the screen?
Looks good. Go to present. Oh, excellent.
Mm-hmm. So now I'd like to start my presentation. I'm Seiko Kita, so I'm a seismologist. So I'd like to introduce a scientific part. So today I introduce the characteristics of the this year's large events near the magnitude 9 event. And I also introduce the relationship between the magnitude 9 earthquake and this year's 3 large events. So this year's large events as this. So this year's firstly February 13 magnitude 7.3 event, and we also have May 1st and March 20 event. These events, the magnitude is near the magnitude 7.0. So here is the magnitude 9 earthquake Tohoku region's location. So before I introduce seismicity, I'd like to introduce nationwide dense seismic stations in Japan archipelago. After the Kobe earthquake, government start to construct the new dense seismic network in Japan archipelago. So at that time, they built the inland stations. So the station distribution of the station distribution. So station distribution, a station separation is 15 to 20 kilometers beneath inland area. And after the magnitude 9 earthquake, government also decide to construct the cabled ocean bottom seismic network stations beneath ocean area. The station separation of ocean bottom seismic network is 30 to 60 kilometers. So now we have the densest or nationwide seismic network among the permanent seismic networks in the world. So, and we can obtain so many results using this seismic network. And this is a map view of seismicity using obtained or using the seismic network. So about 10% of the world earthquake happened beneath Japan archipelago, and most of events occurs at depths of less than 15 kilometers because most of events happen on the plate boundary. So in Japan, we have 4 plates. So continental plate and oceanic plate meet at the trench, in other words, plate boundary. So most of events occurs on the plate boundary. But strictly speaking, we have 4 types of earthquakes beneath Japan archipelago. So one is, of course, plate boundary earthquake. For example, 2011 magnitude 9 Tohoku earthquake. That is an important example of the plate boundary type earthquake. And also we have inland earthquake. This is, for example, Kobe event. So, and we also have outer rise earthquake and intraslab earthquakes. Both events happen within the oceanic plate, but intraslab earthquake happen within the subducting oceanic plate, but outer rise event usually happen in the oceanic plate before the subduction. So this is a list of this year's large events. So February event, magnitude 3.3, 7.3. This is, I use JM magnitude. So this event is classified as intraslab earthquake. And the other ones, the other events are classified as plate boundary events. Though these events have almost the same depth, almost 60 kilometers, but maximum seismic intensity is different because intraslab earthquake tend to have a larger stress drop comparing to the plate boundaries stress drops. So this kind of point of view is very important in the viewpoint of the disaster prevention. And next slide shows the seismic activity of events of magnitude over 7 within 100 years. The left figure shows the sleep areas of large events, and the right figure shows the aftershock areas of the events shown in the left figure. So please see the red contours both of figures. So we can see sleep areas of magnitude 9 earthquake is like this, but aftershock area of the magnitude 9 earthquake is more larger than the area of the sleep area of the magnitude 9 earthquake. So this kind of knowledge is also important for disaster prevention. So and here is this year's 3 large events. So these 3 events also occurred within the area of the aftershock area of the magnitude 9 event. So then now we move on to the spatial distribution of each earthquake. So this is a slide for the magnitude 7.3 Fukushima-ken February event. So the main shocks show as a large red circle, and aftershocks show as a thin red circles. So and the background seismicity show as a gray dot. So we can see red dots maybe the main shock and aftershocks are located within the oceanic plate. So we can say these events can be classified as intraslab events. And then, here is the focal mechanisms of the main shock. So we can say this event happened due to the reverse faulting, high angle fault plane reverse faulting. So this kind of results can be obtained because due to the existence of the newly ocean bottom cabled seismic network existence. So these are station distribution of the ocean area, and these are station distribution of inland area stations. So before the construction of the ocean bottom cabled seismic network, we cannot, we would not determine the hypocentres precisely. So, and we would not classify the events like this. So now we have this seismic network, so we can obtain a lot of scientific results. And next slide shows a spatial distribution of events of May 1st and March and their background seismicity. So the epicenter of the large event show are the red dots. So this event happened very close to the coastal line. So this event, if the this the ocean bottom cabled seismic network is not built, we would can determine these hypocentres precisely. But now we have both of the stations in the inland area and oceanic area, so we can precisely determine the hypocentres, and the hypocentres of these two events can be determined on the plate boundary clearly. So, and based on the focal mechanisms analysis, these events happen due to the thrust type faulting. So, from the point of view of focal mechanisms analysis, these events are different from this February's event. Now move on to this slide. Now in this slide, I'd like to explain generation mechanisms of the this year's three events. So this year's events happen here. So this area is very important. So this area, this event's location is here and here. So this area located between the locked area by a magnitude 9 earthquake and the area of stable sliding area of the two plate boundary. So this stable sliding area is very tricky. This area surely sliding, but does not easily move. So almost locked area. And here is locked area. So in general, mega thrust earthquake happen on the plate boundary, but that movement just happen on the rupture time of the rupturing of the mega thrust event. But after that, the plate boundary is locked very rigidly. So, but here, free area. So, and recent work show and report the seismic slip surrounding the area of the megathrust region. So recent work using the seismic data from the nationwide seismic network in Japan. So these data set show a seismic slip phenomena is observed around the megathrust earthquake's fault plane. So a seismic slip has several indicators. So one is tremor and low frequency earthquake and repeating earthquakes. So in Tohoku region, repeating earthquake is famous as an indicator of a seismic slip. Today, I don't have a lot of time, so I don't explain repeating earthquake in detail, but repeating earthquake usually occur following the seismic slip in the surrounding area. So repeating earthquake is a rupture phenomena, but same patch rupturing and same almost the same magnitude of rupture and almost same waveform released from the same group of the repeating earthquakes. So the distribution of repeating earthquake shown as a blue dot in this left figure. So this blue dot shows the location of repeating earthquakes. Repeating earthquake is a indicator of a seismic slip. So we can see this year's 3 events occurs on the area of the repeating earthquake area. So here. So this year's 3 events happen the area between the rocked area and here a seismic slip happen and strain accumulate also happen on the plate boundary and the portion near the plate boundary in the oceanic plate. So that kind of things is a generation mechanisms of this year's 3 events. So mega thrust events the seismic slip related to the mega thrust event happen, and these events easily can be found and reported. So this is a summary. So today I introduce the events of magnitude over 6 in Tohoku region. These events are classified as an intraslab earthquake and plate boundary events. These are these are examples of the aftershocks of magnitude 9 earthquake. And a seismic slip related with magnitude 9 event may have triggered these 3 events. That's all. Thank you.
Okay, thank you, Dr. Kita. I especially enjoyed your description of the 4 kinds of earthquakes that happen in that region. I found that very informative. Thank you very much for your presentation. Now I would like to move on to our second presenter today. That is Dr. Tomo Mukai. He's a senior research engineer in the Department of Structural Engineering. He will present today on damage to modern reinforced concrete buildings. During the recent earthquakes, few concrete buildings were damaged, so he will supplement his presentation today by showing damage to Japanese concrete buildings from some previous earthquakes. So and also Tomo is joining us from Japan, where it is Friday morning, about 9 o'clock in the morning. So let's kindly welcome Dr. Mukai. Please proceed.
Thank you, Bruce-san. My name is Mukai from BRI, Japan. Now we have a morning session. So okay, today at first, BRI's main role is to support the Ministry of Construction. So they sometimes update the current code or make a new code or so. So BRI groups support their action. So today, And then before my presentation, let me introduce myself. My specialty is reinforced concrete, RC guys, and then we do the damage survey and experimental test. So today I will introduce the damage survey of Fukushima offshore 2020. All right, do you remember Tohoku 2011 earthquake? So we had the mega quake and mega tsunami. So magnitude is 9.0, very huge. And then tsunami height is over than 30 meters. So huge tsunami. And then we had the various damage, building damage. So timber structure, gymnasium, reinforced concrete buildings, and condo and seismic isolation building, and then landslide and tsunami. And very, very many damage at that time. And then 2021, this year, Fukushima offshore earthquake happened. So we have some damage at this time. So BRI survey did after this earthquake. So two groups visited the affected area. One is a timber groups, and then another one is a my group, reinforced concrete group. So at first, according to the report of timber group, some timber housing had damage at the tile roofing in Fukushima and Miyagi prefecture. So Japanese housing uses this type of tile roofing traditionally because this roofing is heavy to resist strong typhoon in summer. But this weight is the weakness to earthquake. So the earthquake occurs, once earthquake occurs, so that this tile drop off. But it's a slight damage. And then second group, according to the result of the reinforced concrete group, so two reinforced concrete damaged buildings in Fukushima prefecture. So one is 3-story library and the other is a 6-story condo. So today I will introduce this damage of two buildings. So keyword is a comparison of the 2011 event, because 2011 quakes shaken this type of buildings. So at that time, this type of buildings had some damage. So let's compare the damage. And then another keyword is horizontal stiffness of structure component. Okay. At first, I will introduce the map of Fukushima. Maybe some audience already knows the location of Fukushima, but let me see. This is a Japan map. So Fukushima is here. Fukushima is south of Tohoku region. Tohoku region is here. And then Kanto region is here. The center of Kanto region is Tokyo. And then now we are at Tsukuba. Tsukuba is in the Ibaraki prefecture. Ibaraki prefecture is the north of Tokyo, around here. And then Fukushima is here, all right? And then magnifying the—
Tomohisa, would you like to go on the presenter view, because we are seeing your next slide and slides are quite small at this point?
Oh, really?
Yeah. We might need to swap screens.
All right, so is it okay?
Yes, perfect now, I think.
Now global screen?
Yes.
Okay.
Thank you.
Okay. Yep. So this is the Fukushima prefecture's location, and then magnifying the Fukushima prefecture here. So there is a lake in the center of this prefecture. And then we visited Koriyama City and Fukushima City this time. So this is magnifying the center of Koriyama City and Fukushima City. And then damaged building is here. And then we have the two strong motion record station near the damaged building in Koriyama. And then regarding the Fukushima City, the center of Fukushima City, this is a damaged building. And then this and this is a strong motion record station. So we have, fortunately, we have the, we can get the data from this station. All right, at first, let's compare the earthquake intensity between 2011 and this time. So Japan Meteorological Agency, JMA, shows a measured seismic intensity. Once in Japan, once earthquake occurs, JMA shows a measured seismic intensity (MSI) on the several media such as TV and Twitter or something. And then 2011 MSI measured seismic intensities show here, and then 2021 here. So the seismic intensity, measured seismic intensity is greater than 2011. So 6 plus and 6 minus is a very big number. But this time, 6 minus or 5 plus is main in this prefecture. And then let's compare the velocity response spectra at strong using the data of strong motion station at nearest damaged building. This is a Korean city, and this is a Fukushima city spectra, and this these two is a 2011 data, and this two is a 2021 data. So regarding Korean city, and then this time we visited the low-rise building, 3-story and 6-story. So natural period is less than mostly 0.5. So now we focus on the range of 0.5, less than 0.5 second. So let's see, let's compare. At first, Korean city, the 2011 velocity response is greater than this time, 2021. And Fukushima city, almost same, or 2011 is a little bit bigger than 2021. It's this is the earthquake intensity of this earthquake. All right. So let's move to the another slides. I introduced the building information. At first is a 3-story library, reinforced concrete library. So this building is old building. Old building means designed before 1981. So in Japan, 1981 is a very unique year because in this year, seismic code drastically changed. And after 1981, the number of the damage of building is quite lower than old building compared to old building. So, but this building is old building, and then in 2011, this building was not retrofitted, and but fortunately, structural damage is very slight. And then 2014. Seismic evaluation is implemented. So the result is no good. So after that, 2017 retrofit work was finished. And then 2021, earthquake occurs. So in 2017, as retrofit work, they added steel braces here, and then they add the polyester seat jacketing here. And then base shear coefficient of this retrofitted building is over than 0.5. So very strong building. And then this area is measured seismic intensity 6 minus area. And then the description of damage is no cracks. But the post-earthquake functional use is no good due to severe damage of some component. And then current condition is to be prepared for repair work in the future. All right, this is the damage distribution drawings. So this is a plan. And then this number 1 or 2 is a damage level of structural component. So for example, this column is damage level is 1. Damage level 1 is a minimum value. And then damage level 5 is a maximum value of damage level. So the seismic retrofit component was added to the frame at north side. This left side is a north side and the right side is a south side. So seismic retrofit component was added to this frame, and then structural component at south side is severe. For let's see, this column damage level 5, this shear wall damage level 5 is a maximum value. So very severe. So horizontal stiffness of component at south side is lower than north side because of the existence of the seismic retrofit work. So let's see the picture. I took the picture on this point from this way. So some tiling and wall had severe damage, and then two single column had severe damage. Let's see the damage of the column. So we can see the concrete cracks. It's cracks due to the bond splitting failure. And then let's see the end of the column. So this picture. So concrete crash, and then longitudinal burr was backling. So, and then let's see the shear wall damage, this one. So very severe damage. So the damage concentrates the south part of structural component. Maybe torsion behavior occurs. All right, let's move next slide. So this is another building. So six-story condo, reinforced concrete condo, an old building designed before 1981. And then in 2011, this building was not retrofitted and still not retrofitted. And then structural damage is slight at that time. So we can see the some wall shear crack or so. And this the base shear coefficient of this building will be around 0.35 to 0.4. This is a minimum requirement of current code. And then MSI, seismic intensity is 5+ area. And then damage, no collapse, but the post-earthquake functional use is no good due to severe damage of some columns. And then current condition is under demolition. All right, this shows the damage distribution drawing too. And this building has two big shear wall here and here. So two shear wall had slight damage. Some columns had severe damage. So let's see the damage of the column, this one. So this column fell in shear, but this wall has very slight damage. So damage level is 1. So this column damage level is 4. So after 2011 earthquake, this wall also had some damage. So some similar shear cracking and repaired. But this repair method is very right one. So maybe some sealing is also. So very right repair. So the column damage is severer than 2011 damage. But as I told you, impact motion is almost same as 2011. So let's consider the reason, the difference of damage. So maybe before 2011, this two shear wall horizontal stiffness is bigger than column stiffness, horizontal stiffness. But after 2011 earthquake, this wall has some shear crack, and then stiffness, horizontal stiffness degrades after 2011 earthquake. So after 2011, maybe column horizontal stiffness is greater than wall stiffness, I guess. So maybe we had better consider the cumulative damage of such type of building. Right. So last slide, concluding remarks. So first one old reinforced concrete building with seismic retrofit doesn't collapse. Current standard works well to prevent the collapse of reinforced concrete old buildings, but post-earthquake functional use is not guaranteed.
So the first lesson is a well-balanced of horizontal stiffness of structural component is needed to keep post-earthquake functional use of this building. Current code doesn't require it. We need seismic retrofit, new seismic retrofit design method to mitigate this type of damage. So second building, one old reinforced concrete building had severe damage and demolished. Some columns at first floor had shear failure. Two shear wall had slight damage. So we got a lesson learned from this earthquake. Horizontal stiffness of shear wall should be properly evaluated after 2011 earthquake. If we had evaluated stiffness degradation of shear wall in 2011 at that time, we could suggest better countermeasures such as seismic retrofit. Thank you.
Okay, very good.
Okay.
Thank you, Tomo, for a very informative and detailed description of these two damaged buildings. I would like now to turn control over to Volkan. He will be able to present questions to our audience members. I have many questions myself, but of course, to the audience, questions take precedent. So Volkan, please proceed.
Thank you, Bruce. Thank you, Tomo. Thank you, Saiko. I have a question from Mehmet Çelebi. He is asking about the situation with long distance effect of the earthquake on tall buildings in Tokyo. Do you have any damage information?
No, we have no damage information of tall building this time. But some building behave elastic state in elastic states. Maybe some people in tall building feels shaking at this time, but no damage.
Great. And could you also share your email address in the presentation?
Sure.
Okay, perfect. Also, can you describe in more detail the column wrap used in the retrofit, the columns? It was a polyester sheeting or something that was, could you explain that a little bit more? How is that working?
Okay. So now you have the interest of the seismic retrofit work, right?
That's right.
Okay. So this one.
Mm-hmm.
Can you see?
Yes. I
so
think it was previous one. Mm-hmm.
Global monitor. Can you see global monitor, big monitor?
I think so. We are just seeing the building description.
Okay. So now this building uses these steel braces. Can you see?
Yes.
Yes. Yeah.
Okay. And then another is a polyester seat jacketing. So some 3 or 4 columns used this type of jacketing retrofit. Is it okay?
Yeah, looks good. Thank you.
Yeah, polyester is a good material compared to the carbon fiber seat. It's cheaper than carbon fiber, but performance is almost same.
Very interesting. Bruce, do you have other questions?
Oh, of course. I have questions. I have a quick question for Dr. Kita. My background is structural engineering, but it seems like after every major earthquake, when I talk with seismologists, they are always surprised. Do you know of any surprises from the recent earthquakes?
I beg your pardon. So,
okay, I'll repeat. Many times when we have an earthquake, seismologists are always surprised. There was some unexpected aspect. Do you have any surprise aspects from recent earthquakes?
Recent 3 earthquakes for me, it's very normal.
Okay.
So
okay, so no surprises.
Yes.
Okay, very good. Then this question is for Dr. Mukai. You showed velocity spectra, and they look similar between 2011 and 2021, the 2 events. am I correct to understand that after the 2011 earthquake, many buildings were retrofitted, and that explains the lack of damage in the recent earthquakes? Is that a correct reasoning? Please explain.
So your question is performance of the seismic retrofitted building compared to 2008?
Basically, it's my understanding there was more damage in the Tohoku earthquake. Mm-hmm. And you mentioned now there was only few buildings damaged, but when I look at the velocity spectra, they are not that much different. So the shaking intensity was about the same. So my question had to do with less damage now because of retrofitting after the Tohoku earthquake. Is that clear?
Yes. In 2011 earthquake, so many buildings already had seismic retrofit works. So almost building, the effect of seismic retrofit work for most of building is good, but sometimes it's a little bit difficult to show the good performance like this library, because this library has do the seismic retrofit work, but so seismic retrofit component added to the only north part. So there is no seismic retrofit work at south side. So the south side is a weakness point of this building. So we can find some this type of building this time.
I have a follow-up question. What was the major change introduced into the 1981 Japan Building Code in terms of seismic design procedure?
In 1981, seismic code drastically changed, and then so after 1981, so we can mitigate the damage, especially collapse damage. We can mitigate. But building doesn't collapse, but building had the severe damage. So once building has severe damage, so everybody cannot use after earthquake. This is a current problem in Japan. We can overcome maybe collapse of buildings after earthquake.
Are there any new seismic codes in the works for functional recovery?
Now, no, but now we need to find the new aspect of the post-earthquake functional use in research.
More questions, Bruce?
I have a question then. This is for Dr. Kita. The question I have has to do with earthquake early warning. That concept is becoming more popular in the United States. It seems to me that your offshore earthquakes are far enough away such that early warning could be quite effective. However, for your earthquakes that occur close by, like the Kobe earthquake, it seems to me earthquake early warning is only of marginal benefit. Do you know about your earthquake early warning systems, and can you comment on what I've just said?
Early warning system. So early warning system was originally made by NIAG. So and that early warning system is effective for inland, intraslab earthquake and plate boundary earthquake, but it's not so good for inland earthquake, Kobe type earthquake, because the hypocenter distance from the epicenter to the station or land area very short. So, but early warning system is very effective for the intraslab earthquake and plate boundary and outer rise region. earthquake.
Excellent.
Mhm.
Excellent. See, in California here, we would have more like your Kobe type earthquakes. So our system might not be as effective as the system you have because your characteristic earthquakes are different. Am I correct to understand?
So classification of earthquakes is very important also for the early warning.
Okay, very good. Thank you.
If you go back to the velocity, oh, go ahead.
How is the difference of the North Ridge earthquake? Is it similar to Kobe earthquake?
To me?
Yeah.
Bruce?
Kita-san.
So I don't.
I'll ask Kita-san.
So excuse me, Kobe and what else?
North Ridge, 1994.
I don't know the characteristics of North Ridge earthquakes.
Okay. Okay, thank you.
Well, it seems North Ridge is what, magnitude 6.7 on our scale, I believe, as I recall. Kobe was about the same as, am I correct to understand?
Yeah, maybe 7.3 or so.
Oh, Kobe was 7.3. Okay,
Yeah.
Kobe was probably bigger.
Yeah, quite large. Okay, for the velocity spectra comparison, could one of the anonymous attendees asking, could the reason of smaller damage be smaller portion of short period component within the Fukushima earthquakes? That's the question.
The reason, eh?
Yeah, the reason of less damage in these aftershocks because of lower short period accelerations or velocity in this case.
Yeah, generally, this in Koriyama City, the input motion is smaller than 2011 in this period range. So that's why many building doesn't have any damage. So only 2 building had damage, I think. So, but we need to identify the reason why 2 type of building had severe damage than 2011 earthquake. Now this is our assignment.
Have you calculated modified Mercalli intensities on these 2 locations?
So location is the same.
Yeah, locations. Okay, locations are the same. What was the modified Mercalli for that for these regions? Do you know? We have the JMA intensity, but have you calculated modified Mercalli intensity for the same location?
Pardon?
The modified Mercalli intensity instead of JMA intensity for these locations, have you calculated those?
So now you are asking the JMS measured seismic intensity, this one?
Yes. So do you also have a MMI version of it, modified Mercalli version of it?
Sorry, I don't know the detail of the.
Okay, no problem.
Seismic intensity, sorry.
No problem.
Maybe Kita-san, no.
Okay, our time is drawing to a close. So we will need to end our question and answer period. And again, the email addresses, I believe each of you put them on one of your slides such that the audience can be able to obtain them. Okay, if not, we'll email when Maggie sends out post webinar information, we'll include them there. Okay, then I would like to thank both of our presenters, and I would like to turn control of our meeting over to Maggie for some concluding remarks. So Maggie, can you please join our meeting?
So we just want to thank everybody for participating today. As Bruce mentioned, you'll be getting a follow-up email with information about how to access the recording. We'll include the email addresses for the speakers if you have any follow-up questions. And there will also be a link to a post-webinar survey. So we really appreciate your feedback in helping us to continue to improve these events. If you're interested in learning more about EERI, you can visit our website at eeri.org. And we want to thank FEMA for their support in making these webinars possible. So thank you everyone for your participation today, and thank you to our great speakers.
Thank you.